Hello there, Mr. Sutton here, bringing you the BC Calculus 617 Part 1 homework solutions on Euler's method. For this problem, f of x is the solution to this differential equation with an initial condition that they've given us. We want to figure out f of 1.4 using Euler's method, starting at 1, going with 2 steps. So since I'm going 2 steps of equal size, to get from 1 to 1.4, my step size has to be 0.2. So I'll first approximate f of 1.2, and then I'll use that to approximate f of 1.4. So starting with f of 1.2, that's going to be approximately equal to f of 1 plus f prime of 1 times our step size of 0.2. f of 1 they told us was exactly -2. They gave that to us. F prime of 1, that's going to be the x value 1 and the y value -2 plugged into my differential equation here. So we've got 1 for x minus -2 for y minus 1. That's 1 plus 2 minus 1, so that's 2. So I've got plus 2 times 0.2. This is -2 plus 0.4, so -1.6, and this was a no calculator problem. All right, so for the next thing, I need f of 1.4, which is what I'm ultimately looking for. That's approximately f of 1.2 plus f prime at 1.2 times 0.2. f of 1.2 was approximately -1.6. f prime of 1.2, that's going to be the x value 1.2 minus our approximated y value of -1.6 minus 1. So that's 2.8 minus 1, which is 1.8. So I've got plus 1.8 times 0.2, -1.6 plus 0.36. That's going to be -1.24, which gives us choice B. On this problem, we have this f of x function that's the solution to this differential equation with 1, 3 as our initial condition. We want f of 2 using Euler's with 2 steps, starting at x equals 1. So since I'm going 2 steps, to get from 1 to 2, I need to go by 0.5s. So I'm first going to figure out f of 1.5, and then I'll use my approximation for that to figure out f of 2. So f of 1.5, which I'm going to call 3 over 2, just because I've got all these fractions in my answers, so I might as well start in fraction form, so it's easier to keep it that way. So this is going to be f of 1 plus f prime of 1 times our step of 0.5, so 1/2 then, I'll write in there. f of 1, they told us was exactly 3. f prime of 1, when I plug in an x value of 1 into my differential equation, I have to plug in this y value of 3 at the same time. So I've got 1 minus 3 for f prime of 1. So that's going to be -2. So we have 3 minus 2 times 1/2. This is 3 minus 1, which is 2. Now we find f of 2. That's going to be f of 3/2, which we just approximated, plus f prime of 3/2 times our step of 1/2. So 3/2, if we plug that in, we get approximately 2. And now f prime of 3/2, well, when I plugged in an x value of 3/2, I got back a y value of 2, approximately. So up here, I'm going to have to do 3/2 minus 2 to do f prime of 3/2. This comes out to -1/2. So over here now, I've got 2 minus 1/2 times 1/2. This is 2 minus 1/4, which is going to be 7/4. Choice C. For this problem, we're given this solution to a differential equation with an initial condition of f of 1 equals 2. We want f of 0 using Euler's with 2 steps of equal length, but now we're starting at x equals 1. First thing to note is that we're going backwards. We're starting at 1, we're trying to get back to f of 0. So that means if I'm doing this in 2 steps, I have to take steps of -1/2 to get backwards. So I'm going to start by approximating f of 1/2, and then I'll use my approximation for that to get f of 0. So this is going to be f of 1, because that's what they gave us for our initial condition, plus f prime of 1 times our step of -1/2. And I'm going to use fractions throughout because I've got those kinds of numbers for answer choices, so we might as well start that way. F of 1, they told us, was exactly 2. F prime of 1, using my differential equation here, I'm going to be doing 2 times the y value 2, because that's what goes with the x value of 1, minus the x value 1. So 2 times 2 minus 1 is going to give us 3 for f prime of 1. So I've got plus 3 times negative 1/2. Well, this is negative 3/2, which if I add that to 2 just gives me positive 1/2. All right, now I'm going to try to go all the way and do f of 0. So to do that, I'm going to need f of 1/2, which we just approximated there, plus f prime of 1/2 times our step size of negative 1/2. F of 1/2 we just found was also exactly 1/2, which is kind of nice. F prime of 1/2, well, I'm going to be doing minus 1/2 in my differential equation, and I'm going to have to do 2 times the y value of 1/2. So 2 times this 1/2 minus this 1/2, that's going to be 1 minus 1/2, which is also 1/2. Boy, they really had 1/2 on their brain on this one, huh? So we've got plus 1/2 times negative 1/2. This is 1/2 minus 1/4, which is 1/4. That gives us choice C. On this no calculator table problem, we're told that y equals f of x is the solution to some differential equation, f prime of x, with the initial condition f of 2 equals 3. Now they've been very nice and given us some values of f prime in this table. We're going to have to use those along with Euler's method to figure out f of 2.4. Now we're starting at x equals 2 with 2 steps of equal size. So to get from 2 to 2.4, I need to go by 0.2s. I'm going to start by figuring out f of 2.2 approximately. Then I'll use that to get f of 2.4. So f of 2.2, that's going to be f of 2 plus f prime of 2 times our step size of 0.2. F of 2 they gave us over here, it's exactly 3. F prime of 2, we actually can get that from our table here, that's negative 0.5, and then we have our step size of 0.2. So this is a no calculator problem, so we might as well just simplify as we go here. So this is negative 0.5 times 0.2. Half of 0.2 is going to be 0.1, so this is 3 minus 0.1, which is 2.9. So careful with your decimal math on this one. Now we're going to go ahead and figure out f of 2.4. That's approximately f of 2.2 plus f prime of 2.2 times our step of 0.2. F of 2.2, we just approximated, that's 2.9. F prime of 2.2 conveniently is in our table, that's negative 0.3. So this is 2.9 minus 0.06, that's going to be 2.84, which gives us answer choice C. For this problem, we're starting with the differential equation of 2x minus y, which we'll be using for the next several problem parts. For this part, we want to figure out the slope field for this differential equation using just these 12 points that they've dotted for us here. So I'm going to set up a table with x values going from negative 1 to 2 and y values going from 0 to 2. All right, I'm going to just go row by row here. Normally I do columns, but let's just switch it up and go by rows. So for this first row, I'm essentially subtracting a y value of 2 from 2 times all these x values here. So I've got 2 times negative 1 minus the y value 2. That's negative 4. 2 times 0 minus 2 is negative 2. 2 times 1 minus 2 is 0. 2 times 2 minus 2 is 2. And these are going up by 2's. All right, next row. Now I'm doing 2 times all these things minus 1. 2 times negative 1 minus 1 is negative 3. 2 times 0 minus 1 is negative 1. 2 times 1 minus 1 is 1. And then we've got 2 times 2 minus 1 is 3. So you might have noticed a little bit of a pattern here that these are going up by 1's. Let's see if that continues. 2 times negative 1 minus 0 is negative 2. And then the rest of these are just going to be 1 more than the preceding row here. So this is going to be 0, 2, and 4. All right. So let me go and actually draw those slopes in. So up here we have a slope of negative 4. And if you need to just kind of ballpark this, I just went like over 1/2 down 2, and that's the same. Next we have a slope of negative 2. Slope of 0 is easy to draw. And slope of positive 2. Next we have a slope of negative 3. So it should be a little less steep than negative 4, but pretty close. Negative 1 is easier to draw. Positive 1 is pretty easy to draw. And then 3 should just be the kind of the symmetrical version of negative 3. Next we have negative 2, 0, positive 2, and then positive 4. Next, I think they also wanted us to sketch the solution curve that passes through the point 0, 1. So here's 0, 1. We have to sketch the curve that goes through there. So trying to follow these tangent lines through here as best we can. We seem to have some kind of parabola action going on here. So that's what I'm going to draw. And there we are. Part A done. For this part, they're telling us the solution curve that passes through 0, 1 has a local minimum at x equals ln of 3/2. They want the y-coordinate of this local minimum. Well, if we have a local minimum, that means that we must have a derivative of 0 at that point, at that x value. So we can actually use our differential equation here. We can say that 0, our slope, equals 2 times this x value minus y. And then we just have to solve for y. So if we just add all this stuff, or subtract this stuff to the other side and divide by -1, we get y equals 2 times ln of 3/2. For this part of the problem, they want us to use Euler's method with an initial condition of f of 0 equals 1, starting at 0, 2 steps of equal size to get f of -0.4. Since we're starting at 0 and going to -0.4, we're going backwards by steps of -0.2. So we're going to start by approximating f of -0.2, and then we'll use that to figure out f of -0.4. So this first one, this is going to be f of 0 plus f prime of 0 times our step of -0.2. F of 0, they told us, was exactly 1. F prime of 0, I'm going to have to plug 0 in for x, and I'm also going to have to plug in 1 for y. So 2 times 0 minus 1 is -1. So we can write minus 1 times -0.2. This is really 1 plus 0.2, so 1.2. Now I'm going to use this to figure out f of -0.4. So that's going to be f of 1.2, or actually f of -0.2. There we go, because we're using this last x value here as our launching off point, plus f prime of -0.2 times -0.2, which is our step here. F of -0.2, that's 1.2. And f prime of that, we're going to have -0.2 plugged in for the x value, so 2 times -0.2, minus our y value that goes with that of 1.2. This is -0.4 minus 1.2, so -1.6. So over here then we have minus 1.6 times -0.2. This is 1.2 plus, this is going to be 0.32, so that's 1.52. Now this was free response, so you actually could have stopped here without simplifying further, but there's your approximated value. For this last problem part, they want us to find the second derivative in terms of x and y, and then determine if we found an approximation that was under or over what we approximated for f of -0.4. All right, so first our second derivative. We're going to have d squared y over dx squared equals 2 minus dy over dx. But they said they want it in terms of x and y. So this dy over dx here has to go. We're going to substitute it out for 2x minus y, which is what it equals. And then we could simplify that if we wanted to 2 minus 2x plus y. All right, next we want to figure out if our approximation from part C was less or greater than f of -0.4. So we need to figure out the concavity at -0.4 for the x value, and then that'll tell us whether we're over or under. So in terms of concavity, we need to know an x and a y value. We had a negative x value that we're plugging in, and for the y value, remember we got, there it is, positive 1.52. So we had a negative x value and a positive y value for our Euler approximation. Plugging in a negative and a positive, we have 2 minus a negative, which is positive, plus another positive comes out positive. So we can tell that our second derivative is positive on the interval from -0.4 to 0. Okay, that means that we're concave up on that interval, which means that we're going to under-approximate the true value. So we can say that our estimation, 1.52, is less than the true value of f of -0.4.